Right. So today we have Alessandro Mininno for this first Quiver meeting of the year, canonically with an Argyres-Douglas topic, and he will tell us about dynamical consequences of one form and two group symmetries in Argyres-Douglas theories. Take it away.
Hello, everyone. Thank you for this opportunity. I was really looking forward at some point to give a talk here. Be kind. And yes, we are going to talk about this, the dynamical consequences of one form and two group symmetry that we explore with my collaborator, Federico Simone Nopadol, in these two papers. And let's start this trip with me. So first of all, since we are talking about Argyres-Douglas, usual thing that I like to do is to take a general approach. You first start, for instance, with the Seiberg-Witten curve of a rank 1 theory. And a very modern way of saying is that you require for the parameter to be scale invariant and up to a certain C-star action. And imposing the homogeneity of the curve, you can classify all the possible theory that for a given conformal dimension, and you end up to have 8 only possible theories, and 3 of them have a fractional scale dimension. And these are the conformal dimension of the Coulomb branch parameters. And these are what have been called Argyres-Douglas theories. Historically, the first one was found for D n equal to theory, in which you can extract the Seiberg-Witten curve studying the Coulomb branch, and you find that this is n equal to n equal to 2 SU3 super Yang-Mills, and there is a Coulomb branch operator of dimension 6/5, and you can compute the central charges, and there is no n equal to 2 Lagrangian description. But and this what would be in the future what I mean by non-Lagrangian theory, in the sense that there is no n equal to 2 Lagrangian description, but there can be n equal 1 gauge theory that flows to in the IIR to this by SUSY, and it gets SUSY enhanced. This is Maruyoshi's. But then any for the n equal to 2 superconformal field theory was a Coulomb branch operator have fractional dimension is called Argyres-Douglas theory. And there is not only rank 1 theory, they can be realized in many setups. And for instance, class S theory, or via geometric engineering or other kind of compactification of other theory. My approach will be focused more on geometric engineering as a type 2B compactification on singular Calabi-Yau threefold. And the usual example is what I will call to be GG prime theory. So the goal of the presentation is to first give you a brief introduction of what is geometric engineering for Argyres-Douglas theories. And then I will focus on 2 main points, that is the dynamical consequences of having one-form symmetries in Argyres-Douglas theory, then the study of the 2 group symmetries in Argyres-Douglas theory, and then also their dynamical consequence, briefly. And what I would like also to end with is to discuss what we called and have been called the bootstrap of DPG theories. And if I have time, I can also discuss how this bootstrap translates if you look at the 3D mirrors. But for time reason, maybe the 3D mirror, I will skip it. So this is the usual content. So let's see. Geometric engineering, what we mean by geometric engineering. And consider type 2B compactification on non-compact Calabi-Yau, and this non-compact Calabi-Yau is defined as the 0 loci of a certain polynomial in C4. For instance, we require that f equals 0 and the gradient is equal to 0 as a unique solution at the isolated point. Then this polynomial cannot be any kind of polynomial, must satisfy some quasi-homogeneous relation whose weights of the homogeneity must be, the sum of them must be larger than 1. And we can study the Coulomb branch parameter of the for D n equal to 2 superconformal theory, studying the mean universal deformation of this polynomial W, of this 0 loci. So in practice, you can take your theory, your F, you deform it by polynomials with certain parameter, and this looks really like a Cyber-Witten geometry, where the parameter represent the Coulomb branch data. The Cyber-Witten differential is replaced by a holomorphic treeform, but then the story is exactly as I showed it in the first slide. You require the homogeneity of the geometry and the fact that the Cyber-Witten differential has dimension 1, and then you can classify all the possible deformation parameters that you have. And there are 3 possibilities. They can be with the conformal dimension larger than 1, smaller than 1, or equal to 1. And the Coulomb branch operator are those with a larger than 1 dimension. Then there are the couplings, and in particular, marginal deformation are those that have a dimension smaller than 1 or equal to 0 in particular, and the masters are equal to 1. Let's see an example. The example is what I call to be GG prime theory. It's a very specific kind of surfaces. Here I am showing, for instance, 2 ADE surface singularity that are FAK and DK, but there can be also E6, E7, E8. And then the GG prime is to choose the F to be the sum of 2 of these surface singularity. And let's take an example. A1, A2 is the specializing this to k equal 1 and equal 2. And you study the deformation, as I was saying before. You ask for the homogeneity of the curve and the fact that the tree form has the dimension 1. And you can find the scaling dimension of the coordinates, and then also the scaling dimension of your parameter. And you see that there is only 1 Coulomb branch operator, which is 6/5, which is exactly n equal to 2 SU3 super Yang-Mills that we discussed at the beginning. But we can be more general. And the idea is that instead of considering polynomial in C4, you can consider it in C3 times C star. One of these variables is a C star variable. And then you modify your theory consequently. You treat it in the same way. And the example of this theory are the DPG theories, in which instead of considering you fix one of the polynomial, but one of the one associated to AP as a C star variable, and the holomorphic tree form is modified. And for example, you have the D2 SUN theory, and you can distinguish 2 of them. So whenever n is even, then they are Lagrangian theory, and they are for Dn equal to 2 SUN gauge theory with 2n flavors. Or whenever n is odd, then the scaling dimension are half integer. So there is no n equal to 2 Lagrangian description, and there are no marginal deformations. So it's an isolated SCFT. What is the relation of this theory with class S? They have a realization in class S. For instance, the A, G theories, they realized in class S of type G with a Riemann sphere with an irregular puncture, and DPG theory is in the similar manner, but with a regular puncture. And upon closing the puncture, you can flow from the DPG to a particular kind of A, G. But this is not the whole story. I mean, the story is very rich. I don't want to overcharge you, but I want to give you all the ingredients that are necessary for understanding what I'm going to say. That, of course, in class S, you can go crazy, and you can consider sphere, which have also twisted irregular puncture, twisted regular punctures. And this allows us to study more general kind of DPG theory, also for not simply laced groups, and also different, even also other kind of isolated hypersurface singularity kind of geometric engineering. And 2 examples are this twisted Dn plus 1 theory of the DP USP to n that we dubbed P USP to n, and they will be one of the protagonists, the main character that we will have in the future when we will discuss two-group theory. So this is my brief introduction of geometric engineering. Of course, I don't think that people that have ever seen geometric engineering will have understood what they are, but at least I hope that I give you a glimpse of what is the idea behind it. So now that you know how to generalize this theory by geometric engineering, how that you know what is an Argyres-Douglas theory, then it's important to introduce another concept, which is this concept of one-form symmetries. So in general, a P-form global symmetry is a global symmetry was symmetry generator is associated to a codimension P+1 manifold, and the charged operator are P-dimensional objects. So our main interest are the one-form symmetry, so P equal 1. They could seem very strange, but actually an abelian for D n equal U1 theory has two U1 one-form symmetry. One is the electric one associated to closed-form currents given by the Hodge star of F. And this is the measuring this electric symmetry is measuring the electric flux through M. And the objects that are charged under this are Wilson lines. Otherwise, okay, of course, you can have also the magnetic symmetry, and which is a closed form associated instead with the F, which is not the Dodge dual. And this is the associated to a magnetic flux through M, and the objects that are charged are Toft lines. Again, this is the main idea, but in Argyres-Douglas, they have been studied in many contexts, and I really think that I'm not exhausting all the list of papers that there are on this topic. But since the Argyres-Douglas do not meet in n equal to 2 Lagrangian description, we need to find a different way to describe the one-form symmetry. And the way in which it's done it is by geometric engineering. For instance, here we can consider GG prime theory on set that are then given by type 2B on this hypersurface singularity X6. And then you consider this manifold that obtained by deforming this X6. And the 3 cycle of this at X6 can be wrapped by D3 brane, and that gives you line defects. And then from this intersection of these 3 cycles, you define a defect group that encodes the information of the one-form symmetry. And this is the main idea. There are plenty of papers. Yes, you see the 14 footnote is the main idea. I will not be able to be better than them and explaining what they are, but in general, you can associate this defect group, and it is possible to split this defect group to the sum of 2 symmetry, one form, which is gamma 1 and gamma 1, and we can call it quite arbitrarily the electric and the magnetic one-form symmetry associated to the GG prime. So in general, we will refer to gamma 1 to be simply a one-form symmetry. From the point of view of the class S, instead, such one-form symmetry can be realized as this defect group with the line defects trapped at the irregular puncture. And by trapped, we mean that the information is in the irregular puncture, because for this, whenever you are doing the Riemann sphere with the irregular puncture, there are no one cycle that you can use to compute the one-form symmetry. So the information on the one-form symmetry must be inside the irregular puncture. So you take any kind of DPG theory and with a full puncture in irregular puncture, and then you close the full puncture. So you are removing all the information except for the one of the one-form symmetry, which is inside the remaining irregular puncture that is giving rise to this GBP theory. For instance, example of one-form symmetry, or the ANEM theory have a trivial one-form symmetry, but you can find one-form symmetry in what we call to be non-Higgsable SCFTs. And these non-Higgsable CFTs are a theory that at a generic point of the Coulomb branch, they are just a collection of any Argyres-Douglas theory at any point of a generic point of the Higgs branch is a collection of free hyper plus a theory without an Higgs branch. And these are what we call the non-Higgsable SCFT. When you compactify, then you look at the mirror of the compactified theory, you will have a collection of free hyper. But the information of the one-form symmetry is encoded inside this non-Higgsable SCFT. And this is... yes.
Just to clarify, non-Higgsable SCFT means there is no Higgs branch.
Yes. So I can be more precise. So a generic point, you can have the Argyres-Douglas reduced to a collection of hyper and CFT with no Higgs branch. So then one can go on and define this.
Maybe I misunderstood. So
yes.
non-Higgsable doesn't mean that there is no Higgs branch, but that the Higgs branch there is a non-trivial theory.
Yes, yes, exactly. Yes.
Okay. So incomplete Higgsing is another word, I guess. Okay, thank you.
Yes. So let me go back. So yes, so this is the idea. So once that you have found that the one-form symmetry is inside the non-Higgsable sector of the Argyres-Douglas theory, then one can use this one-form symmetry to understand the structure of the Higgs branches for the Argyres-Douglas theory. Because any Argyres-Douglas theory with a non-trivial one-form symmetry must have a non-Higgsable sector with the same one-form symmetry, because everything is encoded inside. This is a result that we did in the one of the previous paper. So as a consequence, also, if you study the 3D mirror theory of the Argyres-Douglas theory that has a non-trivial one-form symmetry, then there will be a number of free hyper equal to the rank of the corresponding non-Higgsable CFTs. This is the consequence after. So you start from any Argyres-Douglas theory and you compute the defect loop, you find that is a non-trivial one-form symmetry. Then there must be a non-Higgsable sector which has the same one-form symmetry. If you study then the 3D mirror of this Argyres-Douglas theory, you know that there will be a sector which is given by free hyper, which is equal to the rank of the corresponding non-Higgsable SCFT, and this free hyper may be subjected to a gauging of this one-form symmetry. At the same time, if the theory has a trivial one-form symmetry, then either there is no non-Higgsable sector, or the non-Higgsable sector has by itself a trivial one-form symmetry. Later on, another thing that we discussed plenty in the work and also in other paper have been studied is that the one-form symmetry is also invariant by any kind of Higgs branch flow or Maruyoshi-Song flow. So one can deduce the one-form symmetry from the DPG theory, looking at the theory after that you have closed the full puncture, and then in any case you have a very rich and larger discussion of one-form symmetry also for those theory that are not simply engineerized as a C4 as a Calabi-Yau with a polynomial in C4. And this is the generalization indeed, not because we can study then any hypersurface singularity, and one can compute the one-form symmetry for this general hypersurface singularity GBP, where G can be also non-simply laced. And in this way, we can deduce the one-form symmetry of the DPG theory that flows to the GBP after that you close the function, because these one-form symmetry are invariant under the Maruyoshi-Song flow or the Higgs branch flow. And this is the one possibility. So you study the Maruyoshi-Song flow that gives you this theory here flows to the GP, or you do an Higgs branch flow by mass deforming, and you can, by closing the full puncture, you go from this theory to this. And we concluded that all this theory here, since the one-form symmetry are invariant by this kind of flows, have the same one-form symmetry. And one thing that we explored, extending what this author did in their paper, is that actually one can bootstrap the one-form symmetry. So you can find a one-form symmetry for a big family of theory that are this DCGDP, because they have the same one-form symmetry of the corresponding P theory in which you have C larger than 1. And this is the last part of my talk, and I will discuss it later better. But using the fact that the Higgs branch is invariant under the one-form symmetry is invariant under Higgs branch flow, you can come up with all the possible, you can find a one-form symmetry for all these possible theories. So, are there questions? Otherwise, I will move to the two groups. So this is the first dynamical concept. We understood that the dynamical consequence of the one-fourth symmetry is that since they are invariant under Higgs branch flow, then we can study them for flowing to any kind of flow that we want to do, a Marujoshi-Son flow. And the main point is that if a theory contained a non-Higgsable sector, then you will have free hyper, and having the one-form symmetry gives you the certainty that you will have a non-Higgsable sector. But now we can go to the two-group structure, and not any two-group. We will go look at a specific kind of two-group. For this two-group structure, given as a non-trivial extension between a discrete one-form symmetry and a continuous zero-form symmetry. And this is a very intricate topic, so I will proceed by examples and intuition, more or less. I will be not very formal, but I hope that I give you the idea, the glimpse of what we will. So consider the one kind of the two-group structure theory that, one kind of theory that has a two-group structure that we mean, which is a for d n equal to 2 spin for n plus 2 theory with NF hyper. This has a Z2 electric one-form symmetry, which is the group of the gauge-Wilson lines after taking into account the screening of the matter on the spin for n plus 2 group. And then also the global form of the zero-form flavor symmetry is a USP 2NF mod Z2, where the Z2 arises because there are no generator of the Higgs branch that are charged under the center of USP 2N, which is Z2. So now we have the one-form symmetry, which is Z2, the zero-form flavor symmetry, which is USP 2N mod Z2. And then to compute the two-group structure, we need to look at a very specific short exact sequence, which is relating the one-form symmetry, the center of the quotient in the USP 2N FZ2, and then you complete it with this factor here, which is the maximally trivial acting group on the matter field. How can we see that this calligraphic key is equal to Z4? The idea is that you look at the center of the spin for n plus 2 group, and which is Z4, and then the vector representation transform as a -1 under the generator of the Z4, or a specific generator of the Z4, while the hyper also transform as a -1 instead of looking at the center of the flavor symmetry. So you can consider an element which is combining these two elements here, e to the pi half of the generator of the center of the spin group and the center of the flavor symmetry, and this omega leaves the matter field invariant. And then omega can be interpreted as indeed as an element of Z4, which is a non-trivial extension between the gamma 1 and the Z of the quotient. However, this is not the whole story. What you need to check once that you have identified this element is the second Stiffly-Whitney class that is obstructing the flavor symmetry group bundle, the obstructing the lift of this bundle to the USP, and then also defining the B2 as a background field for the one-form symmetry. You will need to find that the variation of the B2 is exactly equal to the Bockstein homomorphism associated to this exact short sequence applied to W2. And everything is explained in this very nice paper here, and has been also studied later on this paper by these authors. So the upshot of this, up to technicality, is that for the n equal to 2 spin for n plus 2 theory with NF hypers have two group structure, have been proven by these very nice authors. So now, before going to Argyres-Douglas theory, see what happens then that the theory has a two-group structure. Why we should care about two-group structure? And the way in which we justified it is very simple. It's intuitive. The idea is that, for instance, to consider this theory here, which is given by 4 copies of the spin 6 gauge theory with 4 flavors, that we know that has two group structure. Each of them has a two-group structure. Now you consider all 4 of them, and you want to gauge a diagonal USP8 symmetry. Then you can compute the one-form symmetry Z2, 5, and you will find whatever you are going to find. No, so you have this Z2, 5 electric one-form symmetry is given by 4 Z2 given by the spin 6, and then there is the central node that is contributing by Z2. And so far nothing is wrong, because this is something that you can do. But what happens if instead I want to gauge a USP8 mod Z2? And then this is a different story, because now, since there is a two-group structure, then we need to sum over all distinctly witnessed classes with W2, which is the abstraction of class for lifting this USP8 mod Z2 to the bundle of SV8. And then, because of you need to sum over this W2 and the original theory, the spin 6, has a two-group structure that relates this W2 to the background field B2 associated to the one-form symmetry, then not only do you need to gauge, not only you are gauging this object here, but you must gauge also the one-form symmetry of this theory by summing over all B2. So each spin 6 gauge theory with 4 vector, instead of being spin 6, becomes a SO gauge theory with 4 vector, because we have chosen this kind of gauging here. Now, this theory is not conformal. We can repeat the same story in case we want a conformal theory, but the upshot is that the presence of a two-group structure kind of fix the kind of possibility that you can do with your theory. So if you have a theory that have a two-group structure, then whenever you want to gauge a particular subgroup of the flavor symmetry, or you want to manipulate the theory, consider them together, then depending on the object that you are gauging, if it's interfering with the generator of the two-group structure, you are forced then to gauging maybe something else. In this case, also the one-form symmetry. But where Argyres-Douglas come from? No, because the Argyres-Douglas so far is nothing. It's just a story of a two-group. Well, the idea is that there is a specific kind of Argyres-Douglas theory, which is D2 USP8N, where D2 USP8N is given generalized by this hypersurface singularity. That is a Lagrangian theory given by SO for n plus 2 gauge group with 4n hypers in the vector representation. Now, if you fix the gauge group to be spin for n plus 2, this is exactly the same situation that we have before. And this theory has been proven to have two groups, as we have shown before. So we have found a theory in the Argyres-Douglas setup, which is Lagrangian, but still is a DPG theory that has a two-group structure. So the question is, are there other examples of this kind of DPG theory that admit such a two-group structure? Then the answer is that the only DPG theories that can admit a non-trivial two-group structure are the DP USP2M with a specific choice of M, P, and C. In this particular notation, C must be coprime with 2M, and then M and P must be even. They are used to classify the possible object that you can admit. And how can I, if I want to visualize this theory, how can I see it? Well, visualizing in general is not always possible. We can do it for C equal 1, which is a theory that we have seen before. If you specialize the P to be 2 and M also to be 2. And this is the one that we have seen before. But in general, is this tail given by this group. And by this, we mean SO and USP. And since M is even, then the D type, as you see here, as we are trying to make the notation more as possible, clear as possible. Since M is even, then the D type has always odd rank. And so we choose that the polarization so that the SO groups can be can have a global form to be a spin. Then we proceed in the same logic as before. Each spin gauge group has a center Z4, but is screened by a Z2, to a Z2 by the fact that you have a matter in the vector representation. And then each symplectic group has a center Z2, screened completely by the matter in the fundamental representation. So at the end, you will have an electric 1-4 symmetry, which is given by Z2 of P over 2, which is P, where P is the number of D node. And the global form of the flavor symmetry group is USP2M mod Z2. So it doesn't seem very different from the one that we had before. Indeed, there is a non-trivial two-group structure given by the fact that you have a short exact sequence with this object here, and it doesn't split. And it doesn't split because this is very similar to what we are saying before. You just pick up a Z2 factor here, then you will have a P minus 2 over 2 times Z2, and then you have again the trivial, the two-group structure given by Z2, Z4, Z2, which is the one that we had in before. And this is why it's sufficient to put P equal to 2, and you recover exactly the same example that we had found before. And this is a Lagrangian example, and we are claiming that this is true for any non-Lagrangian example. And this comes from a more tricky result, but it's been explored already in this very nice paper that is came up some months before ours, and in which we are they considered basically all the theory that can be engineered by this D in class S by the D-type class S with twisted puncture. And you can study what are the one-form symmetry and the global form for a generic theory. So the monodromy of the Hitching field around the irregular puncture, it gives you the one-form symmetry. And this is computing the defect group for this kind of theory. You can also use bootstrapping or studying of the Higgs branch flow. Then the study of the 3D mirror, for instance, or the global gives you the global form for the flavor symmetry, which is exactly the same. So these two pieces are the same. Now, one can consider, again, the short exact sequence. You can imagine that it's behaving exactly in the same way, but you want to motivate why you can still have this short exact sequence. And this comes from the discussion that this author did, in which we can reinterpret. And they didn't spell it out exactly in this way. This is our interpretation of what they write, that they can come out, they came up with this short exact sequence that involves the trapped electric part of the defect group to a puncture, and then also the defect group to a puncture and the subgroup of defects that can end on that puncture. And this object here have the same value that would have if you reinterpret this trapped electric part as the one-for symmetry. This is the most obvious one, no? Because as I said, the class S interpretation of the one-for symmetry is exactly the trapped defect group in the irregular puncture. So this is the most obvious one. Then you reinterpret the center of the flavor symmetry as the subgroup of defects that can enter in the puncture, and the non-trivial extension is given by the total defect group in the puncture. And they show that this sequence doesn't split, and in this way we can also ensure that our also short exact sequence for a theory that is non-Lagrangian now, with a C larger than 1, doesn't split. And indeed, it has the same structure that the theory that have C equal 1. So we concluded to have a non-trivial two-group symmetry by this, but we are gaining also more insight. We are finding that actually the structure that we found for a theory that was Lagrangian, so the case of C equal 1, kind of reproduce itself also when you are considering more general theory, but they can be related to the Lagrangian theory in a non-trivial way. So this is our motivation of how to group structure arises in Argyres-Douglas theory. We checked all the other DPG theory that are known, and this is the only class that allows for two-group structure, because otherwise the shortest sequence splits. And now that we have defined the fact that the motivation for the two-group structure comes from a relation between a family of theory related by the same value of P and M, but with different coefficient of C, we kind of thought that maybe there was some hidden, more complex, no, than with just classifying the two-group structure, because we found that one-for symmetry were the same when you close the puncture, when you do Higgs branch flow. Then two-group structure were the same when the family of theory is for this theory is the same. So is it maybe possible to extract information about the DPG theory starting from a original Lagrangian, maybe easier theory? And this is what we call bootstrapping, which is again a reinterpretation of what has been studied in details in this very nice paper, which, as you see, I mentioned it. So the bootstrapping of a DPG is that an infinite family of Argyres-Douglas theory can be obtained from an arbitrary DPG theory, but where the theories in the same family share some properties. And the DPG theory that could be can be considered are all this kind, not only simply laced. You see there are all of possible possibilities. In our paper, in the last one, we discussed at length this theory here and this other one. But the same logic can be applied also to other theory, although is more complicated to actually find in an initial Lagrangian prescription, an initial Lagrangian theory. And the idea is to construct this theory is to find what are the family. And the way in which the family are found is to consider the monodromy of the Hitching field, which is controlled by a quantity which is given by this factor here. The presence of the two is not trivial, because we can, for certain kind of DPG theory, we can allow for alpha of the integer P. And so the two doesn't simplify in a trivial way. Then anytime that you can you replace the P of your theory by a factor C, which is multiplying this GCD, and C is coprimed with Q, then you ended up to be in a family of theory that belongs to they belongs to the same family. They have the same Q, and they just are defined varying this value of C that must satisfy a certain relation with Q. It must be coprime. But what kind of property they are satisfying? The property is that all these theory have the same number of mass parameter, the same number of marginal deformation, global form of the flavor symmetry, the one-form symmetry, and the two-group structure. I think that I tried to stress it a lot on the part of the two-group structure, at least for this theory here, the first ones, and also because all the other we show that they don't have it. The one-form symmetry also, the fact that they are invariant under Higgs branch flow can be studied, and one can convince himself that one can obtain the one-form symmetry, but we will see it in maybe one example. The global form of the flavor symmetry is trickier, but one can study the 3D mirror if it's known, and you can study then what is the flavor symmetry of the Coulomb branch of the 3D mirror, and you using Hilbert series and so on, and you can come up with the global form. And marginal deformation and mass parameter have been studied at length by Simone and other people, and you can see that they work in this way. They belong to the same family. So indeed, now it seems very abstract. What I would like to tell you now is that this bootstrapping for the DPG theory is actually has a very specific effect at the level of the 3D mirror. And this is the only thing that I'm going to say for the 3D mirror, also because I am like over time. And the 3D mirror for the DPG theory has been studied at length in many papers, by starting from the one with Simone, Matteo, and Opadol, but then later on we also studied them. And the idea is that you start, for instance, from the easiest one. You start from a 3D mirror of a DDP SU, that if you don't have extra masses coming from the irregular puncture, this is given by the TSU and tail. And in case in which you have also other masses coming from the irregular puncture, then you glue this tail to a complete graph of U1, and the number of U1 depends on the number of masses that you have. So, and together with this, you will have also a sector which is non-Higgsable, that is only given by free hypers. And this is for sure been, you were already seen many months ago by talking from Napadol, and fortunately, I don't have an example explicit. But at the level of the bootstrapping, one can go defining the same kind of notation that we had found before, defining Q, P, and C, all the parameters. You can parameterize it in this way very easily. Then basically the complete graph is given by the number of U1, which are the extra masses, and the given multiplicity. And then you connect this U1 to a tail, and you will also come up, and this is the mirror together with the number of free hyper. The bootstrapping, as we are saying, is just exchanging the value of C, a shift in P, and this shift in P is just reflecting in a shift of the number of free hypers and the number and the multiplicity inside the node. And this is only the shift that you will have. And this is very similar to what you would have for the Maruyoshi-Son flow. So whenever you are shifting P by the Coxeter number, but in our specific case, the Maruyoshi-Son flow is actually a special case of shift, because in our case, we can allow for more general C as soon as they are coprime with the factor Q. But the Marie-Joseph function is simply choosing, in this case, Q plus 1. So let me conclude, and then I will allow for question at this point. The idea is that we discuss the dynamical consequences of having one-form symmetry in Argyres-Douglas. Then we look also at their two-group structure. And I introduced the concept of bootstrapping, but of course, it could be more. It could be done more in some example. But I wanted to give you a taste of how powerful in general are the families that we can construct just considering this bootstrapping. Then. Of course, one can come up with questions like what are the other Argyres-Douglas theory that could have two-group structure, or if there are other kind of two-group structure. If it's not DPG, what else you can have? Or maybe we can look at other kind of symmetries and see if the Argyres-Douglas enjoys also other kind of symmetry, not only one form, two group, or other objects, and that would be nice to study in the future. But for the moment, I think that I will stop here, and I thank you all.
All right, let's thank Alessandro. Do we have questions?
I was so clear that everybody understood everything, and no, there is
so with the theories you're putting on, these theories that share many features, how are they different? So what's the first quantity you compute to say that they're different?
So they differ one of the other by shifting. So you define the factor Q, and then you just replace the P by this factor. So the way in which they differ is at the level of so they can change. It can change the rank of the non-Higgsable sector. And so the number of free hyper in the 3D theory increases, but then you can change the non-Higgsable sector. And then, of course, you can think of it as if you look at the Lagrangian theory, you will have a longer tail, so you will have an increasing in the kind of matter that you can have, right? I mean, they are really they have the same masses and marginal deformation, so the only possibility is that they grow in size of the rank of the gauge group in one theory, or if you look at the 3D mirror, is the number of free hyper that you have in it can be increasing in number. Yes, that's it. They're just bigger in ranks. Yes.
Okay, do we have more questions? Well, let's thank Alessandro again.
Thank you very much. Thank you for having me.
We can go to the unofficial part.